Hello. Today we're going to talk about Unit 9 on solutions. This is an introductory video, so we're just going to go over some basic definitions, take a look at a solubility curve, make sure that we have just a foundational understanding as we move forward in this unit. So we're going to start off today by looking at three different terms that we need to know in order to understand what we mean by the term solution. So the first term up there, you might have heard back in September when we first talked about different types of mixtures and we were classifying matter. So the term solution refers to any homogeneous mixture where the solute and solvent are mixed evenly throughout. Now, solutions don't just refer to solids being dissolved in liquids. They could be solids dissolved in other solids, or gases dissolved in other gases, or gases dissolved in liquids, basically any combination. So if you look at the second term that's up there, a solute, it is the substance that is being dissolved in the solvent. And then that final term, the solvent itself, that is the substance in which the solute is dissolved. So if you think about a typical saltwater solution, the salt, sodium chloride, would be the solute, the water would be the solvent, and together the combination of the two of them would make up the solution. Okay, one of the things that we need to consider when we talk about solutions is this term of solubility. So it says solubility is the ability of one substance to dissolve in another at a given temperature and pressure. We're going to see when we look at our solubility curves graph that temperature and pressure are the two biggest factors that affect how much of a solute dissolves in a particular solvent. Now, in this case, I have the term up there, likes dissolve likes. That simply means that things that are polar, if you think back to when we talked about molecular polarity, things that are polar, like water, dissolve things that are, or solutes that are also polar. So if you think about an extreme case of polarity, something like sodium chloride, which is an ionic compound, that dissolves well in water because water is polar and it's able to pull apart the positive and negative charges that make up a sodium chloride crystal. If you think about something that's non-polar, like a big organic compound, an oil or a fat, that's not going to dissolve very well in water because organic compounds tend to be non-polar. They don't really mix well with things that are polar. All right, our second term, speaking of mixing, is miscible. So two or more liquids that are able to dissolve into each other, they're able to kind of mix completely. So if you think about a mixture of maybe alcohol, which is polar, and water, which is polar, they're going to dissolve really well in each other because they're both polar. Same thing on the other side. If you had two oil type compounds, they're going to mix really evenly, again, because they're both non-polar. If they don't mix well together, that's called immiscible. So if you look at the picture that I have up here, we have basically two examples of immiscible. So this looks like we're pouring some type of almost like motor oil into a cup of water. So motor oil would be polar, or excuse me, non-polar. Water would be polar. And you can see that the motor oil and the water are not going to mix very well. Same thing over here with something like vegetable oil or canola oil, whatever this is. A polar substance and a non-polar substance are not going to be very miscible. They're not going to mix evenly throughout. So now we're going to look at what we can do to help things mix a little better. So you probably know most of these answers already just from, if you think about making coffee in the morning, or if you've ever made lemonade or iced tea mix with your family growing up. So two of the things that you can do real easily to help something dissolve better is increase the surface area. So if you imagine dropping some powdered sugar or crystalline sugar into your coffee, powdered sugar might be a little weird, and you mix it around, two things, the small size of the sugar and you mixing it around both help it dissolve, as opposed to if you took a cube of sugar and you threw in 2, 3, 4 cubes of sugar, it's going to take longer for that to dissolve just because there's less surface area that is exposed to whatever you're dissolving it in. So if you're adding sugar cubes to coffee, there's not as much surface area on a sugar cube compared to breaking up that cube into fine crystals. That's going to help it dissolve much faster. The other thing that you're going to find is that increasing the temperature, for the most part, we'll see not always, but for the most part, increasing temperature is also going to help something dissolve faster. So most things increase solubility when they're at higher temperatures. So increasing the temperature definitely does make something dissolve a little easier. We look at the picture that's behind me, the first thing that you're going to see is that if you were to drop in a sugar cube, you can kind of see the outline of the sugar cube here. Notice that the water is not able to really penetrate it very easily. So we're waiting for just the surface material to break apart before the water can kind of infiltrate further into that sugar crystal. However, if you look at putting like a spoonful of sugar in, notice that the molecules of sugar here are much smaller, and the water molecules are able to surround them a lot more easily than they could in the giant crystal. So breaking something up, increasing its surface area, definitely going to help something dissolve faster, again, along with raising the temperature. Okay, three very important terms when we talk about solubility. So saturated, unsaturated, and supersaturated. You might have heard of the terms saturated and unsaturated sometimes when we talk about fats, and that has to do with whether or not there are hydrogens attached to each carbon, or if any of the carbon-carbon bonds are actually double bonds, in which case the molecule would be considered unsaturated. So a saturated fat molecule with only single bonds, that would be hydrogens, 4 hydrogens basically surrounding a carbon, or carbon-to-carbon bond with 3 hydrogens around each carbon. So if we look at these terms, it's a little different in chemistry when we're talking about saturated solutions. So if you imagine dumping sugar into water, at some point that water is not going to be able to hold any more sugar. That's when we consider the solution saturated. At any point leading up to that point, we would consider the solution to be unsaturated. So if I just drop in a few crystals of sugar into a cup of water, that solution is considered unsaturated, because it can hold more than it's currently holding. As I continue to add sugar to it, it gets closer and closer and closer to that saturation point. And at some point, when I add a spoonful of sugar, the sugar is not going to be able to dissolve anymore, no matter how much I stir it around. And that's what we call a saturated solution. Now, the last term, which is called supersaturated, is kind of tricky. So there's a way that you can essentially kind of trick a solution into being supersaturated. And the way to do that is to heat up that saturated solution and continue to add spoonfuls of whatever you're trying to dissolve. So in this case, let's say we're dissolving sugar. So maybe we raise the temperature of a glass of water all the way up to 75, 80, 90 degrees Celsius, just before the boiling point, and we continue to add sugar into it. Now, we let the solution cool slowly without being disturbed. So if we let the solution cool slowly, there's a good chance that the solution will keep all of that sugar that was dissolved. However, the solution becomes quite unstable. So any type of disturbance, such as tapping the glass or even dropping in another crystal of sugar, could start the crystallization process and cause all of that extra sugar that we dissolved above what was supposed to be dissolved at that temperature to kind of crystallize out at once. That's kind of the idea behind things like rock candy, where you drop in a string and then that sugar starts to crystallize around that surface. If we look at the picture that is below, this is actually the idea that we use in those heat packs. So those heat packs contain a gel of sodium thiosulfate. It's actually a supersaturated solution of sodium thiosulfate. When you flex the little disc inside of that package, that creates the disturbance that causes the crystallization of that heat pack to basically start. Now, the crystallization process happens to be exothermic. So when it goes from this dissolved sugar back to, or dissolved salt, back to a crystalline form, it releases a tremendous amount of heat energy. And of course, we're able to harness that energy to heat up our hands on a cold day. The nice part about this reaction, or this process, is that it's reversible. So if we go back and boil that bag of sodium thiosulfate, we can actually repeat this process a few times. Okay, behind me, what you see is what's called a solubility curve. So the solubility curve basically has a map of how much of a particular solute dissolves at any given temperature. So The y-axis here represents the grams of solute that dissolve per 100 grams of water. So imagine all of this was tested using a beaker containing 100 grams of water. So now, if we look, let's just pick any point on the graph. So here's the line for sodium nitrate. At, let's say, 30 degrees Celsius, sodium nitrate dissolves about 93 or 94 grams. So that point would be right about here. Now, if we increase the temperature from 30 to 40, notice that more sodium nitrate is able to dissolve, and 50, more sodium nitrate is able to dissolve. So that's just confirming what we saw earlier, which is when we increase temperature, the solubility of most, not all, but most substances increases. And you see a general pattern where most of these solid lines go up and to the right. Now, if you look at the key tells you that the gases are actually represented by these dashed lines. Now, the dashed lines all decrease with an increase in temperature. So if you look at the line for hydrochloric acid, here's hydrochloric acid at 30 degrees Celsius, so maybe about 65 grams of it. We jump up to 40 degrees, it decreases to about 62. We jump up to 50 degrees, now it falls below 60 at around 57 degrees Celsius. What we notice about gases is that they actually become less soluble with an increase in temperature. Now, that should already make sense to us, because if we think about a 2-liter bottle of soda, what we do to keep that carbon dioxide dissolved in the soda is to put it into the refrigerator. If you've ever been to a party where they have bottles of soda just sitting out on the table, you'll notice that the soda quickly goes flat. That's because soda left at room temperature, that carbon dioxide is going to basically escape from the soda because it's not being held in. It becomes less soluble at high temperatures, even room temperature. So leaving the bottle of soda out on the table actually encourages the carbon dioxide to escape from that soda. Okay, so now let's take a look at each of these clarification points that I have on the side here. So clarification point number 1 says the curve shows the number of grams of solute in a saturated solution containing 100 milliliters or 100 grams of water, remembering, of course, that the density of water is 1 gram per 1 milliliter at around 25 degrees Celsius. So you could think of it either as 100 milliliters or 100 grams of water. Now, clarification point number 2, any point that you have that is below the line for that particular substance would be considered unsaturated. So let's go back to our example of sodium nitrate. So in sodium nitrate at 30 degrees, we said that this had a value of about, we'll call it, let's say 94 grams. One of the things that you're going to notice is for any of these, there's going to have to be a little bit of leeway on my part in terms of what I can and cannot accept as an answer. So if you picked 93 or 94 or 95 grams, all of those are close enough. There's no way to actually pinpoint it to the exact gram amount. Now, at any point, if I am at 30 degrees and I have less than 94 grams, so let's say I have 80 grams, this would be considered an unsaturated solution of sodium nitrate because 80 grams falls below this saturation point of 94 grams. If I had 30 grams of it, also unsaturated, anything down here would be considered an unsaturated solution of sodium nitrate. Now, if I went above that, let's say I was able to get 120 grams of sodium nitrate dissolved by first heating it up and then slowly allowing it to cool down without disturbing it, creating that supersaturated scenario that we talked about earlier. That's basically the only way that we can exceed the saturation point. So if we look behind me, if I was able to somehow get 120 dissolved without disturbing it, any point that's above the saturation point, like up here, would be considered supersaturated. Now, notice that that supersaturated point is also temperature dependent, because if I move further to the right and I increase temperature, so let's say I'm talking now about 70 degrees. So if I dissolve 120 grams of sodium nitrate at 70 degrees, now I'm below the line. The line for sodium nitrate when I reach 70 degrees is now way up here. So this point of 120 is actually now creating an unsaturated solution. So whether you have a saturated solution or an unsaturated solution or a supersaturated solution is completely dependent on the substance that you're talking about and what temperature you're looking at. Number 4, if the amount of solute is above the line but has not all dissolved, so if you dump in 120 grams and only 100 grams dissolve, that doesn't mean you're supersaturated. That still means you're saturated because you have added more, you've exceeded the saturation point, but you haven't been able to get that to dissolve. So if you look, it says the total grams in solution minus the number of grams in a saturated solution at that temperature would tell you how many grams are just sitting on the bottom undissolved. Number 5, solids whose curves move upward with increased temperature are typically solid because the solubility of solids increases with increased temperature. Now, I would like to point out that there is one exception to that rule. That one exception is right over here with sodium sulfate. Notice the line for sodium sulfate is solid. It's a solid line representing a solid substance. And that solid substance actually decreases. So I'm just going to show you where that is here. That line for the solid substance actually decreases with an increase in temperature. It's very unusual for this to happen, but it is possible. So sodium sulfate actually becomes less soluble at a high temperature than it is at low temperatures. Okay, and the last point, solids whose curves move downward with increased temperature are typically gases like we spoke about before because the solubility of gases decreases with an increase in temperature. They become less soluble at high temperature. That's because they got a bunch of kinetic energy and they're able to escape from that solution. Okay, at this point, I think you have a good foundation of solutions. This was our introductory lesson. So most likely what I'm going to ask my students to do at this point is to try that solubility curve homework, and then we'll go over that. We'll see what questions you have. Thanks very much, everyone. Bye.